We're still taking a look at the Pearson chi-square goodness of fit test, and now we want to apply this goodness of fit test to a normal distribution. Okay, so these are the repair time data that we looked at previously. We had 50 observations. We used the method of maximum likelihood to fit an optimal or an approximate optimal using Excel Solver, mu and sigma to these data, assuming that they followed a normal distribution. And so now we want to know, is a normal distribution really a good fit or not? Okay, so we want to highlight a few different things here: the min, the max, the range, the number of observations, the number of bins, and what that bin width should be. Okay. So let's first find the minimum value. We're going to use the min function for these 50 observations. And we find the minimum repair time was 272 time units. And the maximum is 447.5. Okay, so what's the range then? The range is the max minus the min, which is 174.9. Okay, what's the total number of observations? We know it's 50. Let's just be fancy, use the count function here. You never know when the count function might come in handy if you have some missing values or something like that. If we had an empty cell here, the count function would not count it as an observation. And we have 50 observations, of course. The number of bins would be the square root of 50. Okay, this is a non-integer. What we want to do is round up. Okay, it's just easiest to round up. Number of digits here, number of decimal places is essentially what that's asking. Okay, so we're going to have 8 bins. Okay, so what's the bin width going to be? We got the range divided by the number of bins. Okay, so our bin width is going to be, we're going to round that up as well. Round up. So we're going to have a bin width of 22. Okay, bin width of 22. We don't actually have to round that up if we don't want to. I just want to make sure that we're producing bins that's going to at least be as large as the maximum value here. Okay. So now let's find what the observed values in each one of these bins, each one of these classes is going to be. So here's bin 1. Oh gosh. Here's bin 2, and so on, all the way to bin 8. Okay. And actually what we want to do is also include the min value. So what's the min value? It is 272.6. And to that value we're going to add our bin width of 22. Okay. And we want to hold that cell constant whenever we drag that down. So our maximum value, our maximum bin upper bound on the bin 8 is going to be 448.6, and that captures the maximum value that we have in our set of observations. Okay, so now we have the upper bounds on all of the bins. So now what we want to do is find how many observations fall between 272.6 and 294.6, inclusive of 294.6. Okay. So let's do that. We're going to use the COUNTIF function here. COUNTIF. We've got our range, which is here, range of observations, and our criteria is going to be less than or equal to the value in this cell. Okay. Again, if we were just inputting 294.6, we could do that here without the ampersand. But if we don't want to hard code this thing, if we want to include the cell value, we can include an ampersand and then cell H3. Okay. Also, we're going to want to drag this thing down, so we need to put dollar signs in front of our ranges because we don't want our ranges to change whenever we drag this current cell down. Okay, so what do we see? What are we seeing here? We're seeing that 6 observations fell below and equal to 294.6. Okay, so now let's implement this equation again here. However, this is a cumulative value, right? This is the cumulative number of observations, the cumulative distribution of values below and equal to 316.6, which is not what we want. We want what lies in between these two values. So we need to subtract off this from here. Okay, so we had 8 values that lie in between 294.6, greater than 294.6, less than or equal to 316.6. Okay, and so on. So hopefully, whenever we sum these up, we'll get something like 50. And we do. Okay, so we've included all of our observations in those 8 bins. And that's a good thing. Okay, that's a good self-check. Now, let's find what we would expect to see if the distribution is a normal distribution. Okay, so in our previous example with an exponential distribution, we used the CDF of the exponential distribution to find the probability associated with each one of these bin ranges. Okay, but here we have a built-in Excel function for the normal probability distribution. So that's a good thing. Okay, we don't have to hard code in any sort of distribution. Okay, so let's do this in separate steps. Okay, just so we're clear on how we're demonstrating this. Okay, so let's use the norm dist function. Okay, the norm dist function is going to give us the probability associated with this value on the axis when the mean is that mean value that we calculated from the method of maximum likelihood. So we need to input those in first. Okay, let's remember what those are. If you go back a couple of videos, you'll find that the mu that we found from the method of maximum likelihood was 345.472. And the value of sigma was 43.17852. Okay, so those were the optimal values from the method of maximum likelihood if we assumed that these data follow a normal distribution. Okay, so now let's find what the expected value of bin 1 would be given a normal distribution with those 2 parameters. Okay, this is exciting. So let's go to the norm dist function again. Okay, what's the cumulative probability up to the value 294.6 when the mean is this and the standard deviation is this, and we want a cumulative probability distribution. Okay, so what's the probability? 0.119. Okay, 11.9% of observations lie below 294.6. Okay, and that goes out to negative infinity. Okay, so what would we expect to see then? Well, this value times 50. Okay, this is the number of observations that we would expect to see in bin 1 if these data really follow a normal distribution with these 2 parameters. Okay, what do we see? Well, the actual observations, 6. What we expect to see, 5.968. Okay, really close. Very close here. Okay, that's a good thing. That's a positive sign. Okay, so now what we want to do is drag these down. Okay, so we're going to have to hold these 2 cells constant over here. So let's put our dollar signs in front of those 2 cells for the mean and the standard deviation. And remember what would happen if we drag this down. Okay, if we drag this down, this is going to give us the cumulative probability below and including 316.6. Okay, that's not what we want, right? We don't want the cumulative probability to there. We want to subtract off that one. Okay, we just want what's the probability inside bin 2. So let's take this value and subtract it from this value. Okay, so that's the probability inside bin 2. If we multiply that by 50, That's the expected number in bin 2. Okay, so we would expect to see 6.62. We really saw 8. Okay, not bad. And so let's keep dragging all these down. So here's the probability up to here. Okay, let's go ahead and just sum this up and see what we get. Hopefully it's close to 1, but it's not going to be 1 exactly because we're not including probability all the way up to positive infinity. We're truncating our probability off at 448.6. So what we need to do here is alter this equation, okay, to just be 1 minus the probability less than here, less than or equal to here. Okay, if we do that, that gives us the probability of everything greater than 426 up to 448.6 and then all the way up to positive infinity. Okay, everything larger than 448.6 is going to be small, but we still need to include it just so we're accounting for everything. So when we do that, our sum of probabilities gets to 1. Okay, and let's drag this on down. This gives us the expected values in each one of those bins. Okay, so now we have the actual observed values in each bin, and we have the expected values in each bin. And so now we can implement our goodness of fit test statistic. Okay, so let's bring this down to here, and let's calculate those differences. So here's the observed minus the expected squared divided by the expected. That is not quite right. There's the observed. Observed minus expected divided by the expected. That looks much better. And we'll do that for all 8 bins. Okay? So what we saw, quite a deviation here. There we saw no observations in between or greater than 404.6, less than or equal to 426.6. Saw no observations there. Okay, what did we expect to see? 2.75. So not quite what we wanted, or not quite what we would have expected to have seen. However, that's out in the tail. Okay, so that's bound to happen. So we're going to have a large deviation there, and we're going to have a somewhat sizable deviation in bin 8. Because we actually saw 3, and we would have expected to see 1.5. Okay, so now let's calculate what this test statistic would be. That's the sum of those deviations. Okay, 6.133. So now we got to find the p-value. Okay, this one is kind of iffy. We're not entirely sure what we might do here, but let's calculate the p-value. Okay. That's going to be with that chi-square dist.rt function. Okay, chi-square dist.rt. Okay, the value on the axis and the degrees of freedom. Okay, degrees of freedom here are going to be 8 minus the number of parameters in the distribution, 2 minus 1. Okay, that is k minus the number of parameters minus 1. K is 8, number of parameters 2, mu and sigma, minus 1. And that's our p-value, 0.29. Okay, pretty large p-value. Larger than any alpha we would choose. Let's remember what our hypotheses would be. Okay, the null hypothesis is that the data follow the distribution that we're interested in. That is a normal distribution. Alternatively, the data do not follow a normal distribution. Okay, so p-value large, do not reject the null, conclude that the data do indeed follow a normal distribution. Or at least we don't have enough evidence to suggest otherwise. Okay? We're not saying that the normal distribution is the very best distribution. There are other ways that we can do that kind of thing. Okay? All we're saying is if we have a candidate distribution, a normal distribution should be among the candidate list because there's no reason to believe that it's not a normal distribution. Okay? These differences aren't enough to lie in the tail, lie in the upper tail, lie beyond a critical value, okay, the p-value is still sufficiently large. There are many goodness of fit tests for a normal distribution. This is a very simple one. Okay, there are better ones in the literature that you can now go look up if you would like to implement something else. A lot of software packages implement other tests. For pedagogical purposes, the chi-square goodness of fit test, the Pearson chi-square goodness of fit test, is a good one to learn, but there are some that are more sophisticated, like the Kolmogorov-Smirnov test. Okay, that's one. Anderson-Darling is another. There are many tests for normality. Okay, you'll look up tests for normality on the internet, and you'll find all kinds of tests. This is a very popular one, though. Okay, it's a little more sophisticated, a lot more sophisticated than this very simple chi-square goodness of fit test, but this gets the job done in a lot of cases. Okay, so this is a goodness of fit test for normality. After we've performed method of maximum likelihood to find mu and sigma, we can actually test to see if this is a good distribution to be using in the first place.